Let's consider another example with a more substantial net force function. This function describes the net force on an object of mass m, which is falling toward a planet of mass big M. So the falling object has mass little m, the planet has mass big M, and r is going to represent the distance, the changing distance of the falling object from the planet. Now, just to make the notation more familiar, I'm going to, instead of r, we'll just call this distance x to avoid possible confusing connotations with the letter r. So I'm going to change the name of the variable from r to x, but it has the same meaning, and this equation could certainly be solved in the same manner with the variable r, and I'll kind of indicate that at the end. So that our net force function is this. Capital G is the universal gravitational constant. The negative is because if we're at a positive distance, our net force is going to be toward the planet in the negative direction. Now we have a choice of two functions, two ways to represent this function, or two ways to represent our differential equation for the velocity function. Okay, we could write it as m dv dt equals this expression, or mv dv dx equals this expression. Here the variable is t, whereas our force is given in terms of x. So we're going to have three variables here, three quantities. We're going to have v, t, and x, and no understanding or no specific relationship between t and x. So that's not going to be a good choice. We're going to choose this one, where our dependent variable is x and our function is given in terms of x, and we can easily see that we're going to be able to separate the variables. We're going to have dx over x squared, and we're going to have v dv over something else, and even more conveniently, well, of course, either way, our mass little m is going to divide out. So what do we get? Looking for the marker, don't have the right color, we'll use this one. Okay. Separating the variables in the second equation, second form of the equation, we get v dv on the left hand side. On the right hand side, we're going to get negative big G times big M over x squared dx. Both of these sides are very easy to integrate, so we integrate this side and we end up with v squared over 2. On this side we integrate and we end up with what? The integral of reciprocal of x squared is the negative reciprocal of x, so we're going to end up with gm over x plus some constant. Solving for v, we see that v is going to equal the square root of g m over x plus our integration constant. If we put an initial condition on this, the condition that v at, let's say, 10 equals 0, then we have v of 10 equals the square root of gm over 10 plus c, and that should be 0, meaning that c equals negative gm over 10, and our velocity function would be square root of gm over x, and it's so in the habit of writing t for my variable. let's simply eliminate that with a coin. So we get gm over x minus gm over 10, so that v of x could be written as the square root of gm multiplied by the square root of 1 over x minus 1 over 10. With this function, we could answer the question of how fast this object is moving when it's a given distance from the planet.